All right, welcome everybody, and thank you so much for joining Ask Why. My name is Simon Reuning, and I'm the Global Technical Marketing Manager for YAGEO Group. With me here on the call today, I have again Alexander Nebel, who is the European Technical Marketing Manager. And we do have an exciting topic for today, and we're going to look at how no part is perfect. Looking at the components, oftentimes in our applications, they're not going to be in ideal conditions, and the products aren't ideal. So we're going to look at some of the parasitics and get a better understanding of how our passive components actually behave in the real world.
Yeah, well, this is how we know what a capacitor looks like, or at least what we have learned in school or during our studies. But unfortunately, this is not the full truth. A capacitor has even more parts in it, which is sometimes even more confusing. So the ideal capacitor has an ESR and an ESL. These are parasitic effects that come in addition to the capacitor. For example, the ESR can be the length of a piece of wire, but also the ESL. So the ESL will include a partly inductance, which comes on top of the capacitor, and also the ESR is the length of the wire from the board connection to the electrode itself inside the component. So, and normally these parasitic effects are unwanted. We want to keep them as low as possible if this is for our application needed. So here we come to the next point where we see, okay, the capacitor model includes ESR, ESL, and even more.
So when we start looking at the ESR, you can see that it actually has an effect as far as it goes with frequency. You will see that the ESR is going to be lower at higher frequency ranges. You can also see that the ESL is going to have an effect. Now, here in our example, that's of course going to be in the high gigahertz range. So that means it's not necessarily going to be a problem for most applications. But if you are working in that high frequency range, that could potentially be a problem. And then here we also have the DC bias effect. So now the DC bias effect, that's actually something near and dear to my heart because I have run into an issue with that in my design career. One of the power supplies that we have designed needed to have a certain ripple at the output. And of course, being the good designer, I simulated the circuit ahead of time. I made sure that all the capacitor values and everything was functioning as it was supposed to. Now, once the product was actually finalized, I ended up running the test and was not meeting my spec on the ripple on the output. So that was a huge problem because I did everything right. I looked at the capacitor, I looked at the values, but the DC bias effect was messing up my end result. And so that's something that you really need to consider when you start looking at the capacitor because the applied voltage in your application is going to have an effect on those capacitors as far as it goes for class 2 or less capacitors on the MLCCs. So if you are using MLCCs on your output for filtering, you really need to be considering that because it can really cause you some issues that you may not be easily solved. They may not easily be solved unless you start switching to different technologies, and that's not always the case, especially if you're limited by space or voltages. So when you start looking at the DC bias effect, make sure that you understand it on the capacitors that you utilize in your applications. But that's not all. We also have some parasitics on our resistors.
Yeah, and again, this is similar to what we have seen with the capacitors. So even if you take the resistor and we see the ideal resistor model, which only is a resistor, but again, also we see here some parasitic effects like capacitance and inductance, which come on top. So, and again, for sure, the inductance comes again with the length of the wire. And we can see here on the table different technologies where you can also see the different parasitic inductance values. So if you take an resistor with wire wound technology, then the parasitic inductance is quite high. Whereas if you take a film technology, then the parasitic inductance is very low. And the same is also for the parasitic capacitance. So again, a wire wound technology, because simply said, the item is very big, it has a very high parasitic capacitance, and the SMD, or in general the thin film resistors, have a very low parasitic capacitance.
I don't know, Alex, one of the things that we don't see on here is the power rating, but I remember you have a really great story with a customer as far as it goes on the power rating. Can you share that story?
Yeah, well, this is a very interesting story because typically a customer might think it's enough to think only about the resistance value and the maximum power rating, and then it's enough. But what actually happened in this example was the customer didn't consider his maximum temperature. And the ambient temperature of this application was quite high. It was around 100 degrees. And at 100 degrees, we have a D rating, which we can see here that the D rating starts already at 70 degrees. And at 100 degrees, it goes down to 60% of the maximum power rating. So choosing the right power rating of the resistor wasn't even enough because he didn't consider the right temperature values. So here we need to choose a different part or with different technology or with a higher power rating.
Yeah, and here's just a good example that if you choose another product that is not only rated to the power that you need for your application, you also need to pay attention to what is my operating temperature range. So here on that graph, you can see this product would have been the right choice for that particular customer because they could have run this product at 100 Celsius and still had 100% of the power rating for this product. And this is actually one of those errors. When that resistor fails, it might not always be a critical failure. It might just be that the resistance is changed over time because it is run at a non-data sheet spec condition, and that will slowly damage the product. And that doesn't always mean that the product is just going to blow up, which is, in that case, of course, we know right away we made a mistake. But sometimes this is one of those errors where the part slowly is damaged, and we may not know right away that there is an error until you see, hey, my product isn't functioning the way I intended. So what's going on? So make sure that when you start looking at power ratings for your resistors, that you do consider the operating temperature as well. So for the last part here, we have inductors.
Yeah, well, and the story is the same. So we have an inductor model, which is the ideal inductor, which we know. But again, we have some parasitic effects. We have a parasitic capacitance, and this is very simple to understand because you have many turns on your inductor, and between each turn you have a capacitance, unless you have a huge distance. But typically components are very small. But also we have two capacitance, a resistance value which come on top, the ESR and the EPR. The EPR is coming from the core loss, whereas the ESR is mainly coming from the wire loss. And this is what has an additional impact on the component, which might be a not wanted effect. So what we see here is a screenshot out of the data sheet. So we can see different values. Again, we see the inductance and the inductance value, but the DC resistance, this is what is the resistance of the part, which comes from the length of the wire and also the cross section. And the DC resistance mainly is an indicator for the IRMS, for the rated current, which is somehow the self-heating of the part. So we have here a certain self-heating at this current value. And then we see the saturation current. And you see here two different saturation currents, ISAT2 and ISAT3. And this is depending on how much capacitance drop, inductance drop, not capacitance drop, inductance drop you have at a certain current. So the one is at 20% and the ISAT3 is at 30%. So depending on which value is more relevant for you.
Yeah, and that's also something that might depend on what the datasheet spec states. So for us in this particular example, it just means 20 and 30%. But if you have other materials, other products, it could be 10 or 15%. So just look for a little note on the bottom of the datasheet that will typically point you to exactly what does ISAT 1 and 2 and 3 mean. Right, but that's not all that we have to consider. We also have to look at the core material. Can you talk about this a little bit, Alex?
Yeah, right. It's very important to understand also the behavior, because the rated current, the saturation current ISAT and I1 and 2 and 3 just give an indication of 1 point on a curve. And we see here two good examples. So one is the ferrite and one is the metal composite. So what we see here in green is ferrite material. And we see that typically ferrite material has a very stable inductance value until we reach a certain current value. And then we have a huge drop. And dependent on what is your output current and your ripple current, which comes typically on top of your output current, you might be at the point where immediately the inductance value will drop. And at higher temperature, which is comes additionally to that, the maximum current will be reduced. So whereas if you take a metal composite material, which is the gray curve, this is not that steep. It's very stable. And we see here that if you have a higher current, then there's not this huge drop of inductance value. So the metal composite material seems here to be more stable for higher current values. And this is very important to understand which material the customer is using here.
Yeah, and I don't have a particular example for somebody running into this issue with a ferrite inductor, but I've had customers that were using transformers that had ferrite cores that were actually running into this temperature issues. And so if you start looking at the graph, you can find that at different temperatures with ferrite materials, you will have different saturation curves. And if you don't fully consider that, you might be designing a product at 25 Celsius, but there's effects that will happen in your power supply. The product is going to run maybe at 25 Celsius, maybe your ambient temperature will be 45 Celsius. But that's not all. As the power supply is going to run, you're going to have some losses in that core, and that's going to cause self-heating. So that means that core material is actually going to run significantly warmer than you might expect. And if you don't consider that in your design, you could get into a thermal runaway situation where you start getting hotter and hotter because now your inductance is going to drop because you're running into this soft saturation of your transformer. And so now you're getting into the thermal runaway where you start getting hotter and hotter and hotter, and the inductance value is going to drop and you're running less efficient, and eventually something is going to blow up. So again, this is really important to consider your materials that you use for your inductors, because there's all kinds of different options available for you. There's high temperature ferrite options if that's a problem for you. There's also going to be high permeability options. There's also material options like metal composite that give you the hard saturation, soft saturation. And then there's also nanomet material, which allows you to have high permeability and soft saturation. Now, of course, all of these products are going to have their best use case. But again, you need to consider that before you start doing your design. And one other thing to do is to actually simulate your products. And we do offer a really great tool. We have our YSIM tool available for free on our website. You can easily go to our website and take the product that you're going to use in the application, and you can simulate everything ahead of time before you actually start putting this product on your board. And that makes it so much easier because it saves you time. It's just one click away, and you can very quickly see exactly how this product is going to perform in your application. Not to go into too much depth, go ahead and play around with it. Again, it's a free tool. You can check it out and see what it can do for you. But you have the option to really look at the impedance and the ESR over the frequency. And it's not just in a lab situation. You can simulate it based on the ambient temperature. You can simulate it based on the bias voltage of your actual application. So that makes it very useful. You can also check what the capacitance and inductance are going to look like. When do you enter which region? What's my frequency dependency? You see, what's my limit? What can I run this capacitor at? You can start looking at the current and the voltage rating of those products. You can even simulate the S11 and S21 parameters. But furthermore, you can download a real SPICE model. You can download the capacitor model as a real model, not just as an ideal model that you typically find in simulation tools. And you have the option to look at what the capacitor versus bias voltage will look like. And when you start simulating those types of products, you will very quickly identify, hey, this product actually has significantly lower capacitance at the voltage that I'm going to run at. Is this actually going to work for me? Maybe you have to go with a different technology. Maybe X7R is not the right choice. Maybe you have to consider using a COG product and use more than one of that. And of course, lastly, you can also simulate what the temperature rise and ripple current will be on those products. And we offer you a graph that can give you an idea of what the self-rising temperature is of the product and what effect it has to your ripple current capabilities. So again, simulate the products, go check out our website, and we make it very easy for you to use our products and implement them in your final design. And this will help you avoid a lot of the issues that you might run into later that could potentially be very costly. So with that, that's everything that we have for today. And I hope that everybody can see past the ideal conditions of our components and of the passive components and starts looking at the data sheets from a different angle and really looking at some of the issues that we discussed today. So until next time, I just want to remind everybody to keep on asking why.